In this video, we'll be covering partitioning a line segment into a given ratio. We have two objectives. We're going to start with the easy type of partition. We'll partition line segments where one of the endpoints of the line segment is at the origin. And then we'll look at the more general case of partitioning a line segment into any given ratio. So in this first example, let's suppose we have a segment AB, and suppose that the endpoints are A is the origin, and B is the point 14, 17. X is 14 and the Y is 7, 14, 7. And what we want to do is we're supposed to find a point P that partitions or divides the segment into two different segments whose ratio are 3 to 4. So another way to write that out, what that's saying is we're looking for the point P so that if I did the length of AP and I divided it by the length of PB, we would get the ratio of 3/4. Now, in order to do that, we really want to actually look at the ratio of AP over the whole thing, AB. What would the ratio of this divided by the whole thing be? Well, since we know the ratio is 3 to 4 here, we could actually label this piece as 3 times some number A, and this would be 4 times some number, just like we've done in previous examples. These two segments would then have the ratio of 3/4. This then enables us to write down what this ratio is. So AP would still be 3A, and then AB would be the whole thing. It would be 3A plus 4A, which we could simplify this to 3A over 7A. In other words, it's 3/7. Now, this is something we're going to be doing in general, so we really didn't need the A at all. Really, this ratio came from just doing 3 over the 3 plus 4, and that's how it's going to work in general. Whatever this ratio is, the one that we're really going to use is going to be the numerator divided by the sum of the two. The way you want to think of this number here is this is really acting as a scale factor. Well, where is that scale factor coming from? Well, the way to see this is if we drop down vertical segments from these 2 points, you would see that we have two triangles here. We have this small triangle, and then we have the large triangle. And we know that those two triangles are similar to each other because the vertical lines that I drew are parallel to each other, which ensures that they are similar. And if they're similar, they have a scale factor, and the scale factor would be the ratio of two corresponding sides. Well, in those triangles, AP and AB are corresponding sides. This is part, and then AB is a whole. So part to whole. So this really represents the scale factor. Now, our goal is to get the coordinates for P. Let's say that P has the coordinates of X and Y. Well, one way to think about that is the X is actually the length. Let's use a different color so you can see that. X is the length of this segment right here. Right, that would have to be X. And then this is the Y value. And if this is the scale factor, then what that tells us is that X would have to be 3/7 multiplied by this segment here at the bottom, multiplied by this length. Well, how long is that? How long is it from A out to this point here? Well, we actually know what it is. This is just the X coordinate for the point B. This is 14. So to get the X coordinate for P, all we would have to do is take the scale factor, and multiply it by 14. This segment here has to be 3/7, 3/7 of 14. Take 3/7, multiply by 14, you get X. All right, so if we go ahead and do that, this just comes out to 6. Right, the length of this segment has to be 6. We can do the same thing for Y. The Y value would be the scale factor multiplied by this side here, which in this case is 7. So if we take 3/7 times 7, we end up with just 3. So that gives us the value for point P is really just 6/3. Now let's break down what we really did to get this. There's a kind of a different way of writing this. You could think of it as we just applied an operation on the point B itself. What we did is we took the scale factor, 3/7, and we multiplied it by the point 14.7. And when I say multiply, I mean we multiplied each coordinate. So what we really did was 3/7 times the point B. And then let's remind ourselves, where did 3/7 come from? Well, 3/7 came from the original ratio. We broke it down as it was 3 divided by 3 plus 4. So this process that you see right here is going to work in general. So let's try to generalize that. So the next example, same exact problem, except I've just put in general coordinates for B. I've just said it's point x, y. But we're going to do the same procedure that we did before. So the first thing to do would be to find the scale factor. So the scale factor is going to be AP divided by the whole segment AB. So this divided by the whole thing. Well, we know that we were given, should have written that down, AP divided by PB is supposed to be little a over b. The ratio is, think of this as like A and this is like B. This to this. So if I want the overall scale factor, the numerator is A, but the denominator is A plus B. AB would be the whole thing. So here's our scale factor. So according to what we wrote on the previous slide, to find the coordinates for P, let's go back for 1 second. All we have to do is take the scale factor and multiply it by the coordinates of B. So it's just going to be A over A plus B times the point B itself. And this really is the answer. If we wanted to write it out with actual coordinates, oops, this is supposed to be a lowercase b here. Can't mix those up. Right, this is the point B, and this is just the number from that ratio. All right, so I said the coordinates for B were x, y. So these just represent numbers, and you could think of in multiplying each of them individually by that. So you could write it as A over A plus B times whatever that x coordinate was, and the same thing, A over A plus B times the y coordinate. So this is a formula that would work in general, but it only works when one of the endpoints is the origin. So this is definitely considered the easy case, but only true when one of the endpoints is the origin. Okay, so that's just rewritten out here. And again, just really want to emphasize this is only true when one endpoint is at the origin. Okay, so let's try to do a more general example. So in this example, we've got segment AB again, but neither endpoint is at the origin. Just two random points in the plane. But again, we want to find a point P that divides the segment into two segments whose lengths have a ratio of 2 to 3. Now, the way we're going to do this is we're going to change the problem into the first type of problem, meaning that I'm going to recreate this segment so that one of the endpoints is actually at the origin. So how do we do that? Well, the first thing we have to do is identify which point is going to be moved to the origin. And really, this is one of my complaints with how this stuff is handled, especially on Plato, is really we should only be doing this with what's called a directed line segment. Or some people would call them vectors. So what we mean by that is on these problems, they really have to tell you like a direction. They have to say from A to B. And that's just the convention we're going to always use. A is always going to be our starting point. B is going to be the ending point. So what that means is, the takeaway from that is, I'm always going to transform A back to the origin. So the goal is take this directed segment and shift it so that A is back at the origin. Well, how far did I shift it? In order to do that, I had to go down a certain distance and then I had to go back. Well, how far did I go down? I went down 2 units. You could think of that as a -2, and I went back 4 units. Think of that as a -4. Another way to think of this is I just subtracted this point from A. I took A and I subtracted itself and it took me back to the origin. Well, to get to where B needs to move, I have to do the same thing. I have to go down 2 and back 4. A different way of thinking about that is the image of B, that's what I mean by B prime, where it gets sent to, is really found by taking B and subtracting A. You just take this point and you subtract this point. So what that would look like is you're going to take the x's, subtract their x's, so 9 minus 5, or sorry, 9 minus 4, you get 5. And then do the same thing with their y's, 12 minus 2. So that gives us the image point of 5, 10. So this point right here is really 5, 10. Okay, so let's make sure we're clear on what we've done here. All I've done is I've taken the original segment, this directed line segment, and I've transformed it so it's back here at the origin. These have the exact same length, they point in the exact same direction. So what we'll do then is we'll perform the procedure that we did before on this segment. We will find the point, which we're going to call P prime, that divides this into the ratio of 2 to 3. Once I have this point, then I simply shift it back to the other line. And we shift it in the same way. We're just going to go back up 2 and over 4. Same way that we shifted down 2 and back 4. Right, that will just transform us from one point back to the other. From one segment really back to the other segment. So let's find P prime. Now we get to use the strategy from the previous problem because now we have an endpoint that is at the origin. So using that formula we had before, P prime has to be the scale factor, which is going to be A over A plus B, times this time B prime, because we're using this thing here. To find that point, we take the scale factor, we multiply it by B prime. So in this problem, scale factor would be 2 over 5, because you have to add the A and the B together. And then B prime we have sitting right here. So 5, 10. Multiply each component, so you've got the image of 2 and then 4. So this point right here is really the point 2, 4. But that's not the one we want. We want the corresponding point back over here. So I need to move it back over. Now, think about how we moved in this direction. To move back to the origin, we just subtracted A. So to move back to the line we want, we have to add A back in. So what we're really doing is we're going to take, to get P, we take the P prime and we add A back in. We subtracted A to get back to this line segment. We're going to add A to move back to the one that we want. So this was our P prime, so 2, 4, and then add on A. A was 4, 2. And that gives us the point 6, 6. So the coordinates for that point are 6, 6. Now, just to verify that this actually works, let's try doing this in GeoGebra. Okay, so I've gone ahead and put in our segment, our directed line segment AB, and let's go through the same procedure, but we'll make GeoGebra do the work. So we said B prime is supposed to be B minus A. And you can see B prime over here, 5, 10, same point. Then A prime is just the origin. You could think of it as it's A minus A, but that is obviously just going to be, equals A minus A. Obviously that's the origin. Let's go ahead and connect those with a directed line segment. So one thing I want to show is that no matter what now, if I move this point here, you can see those always point in the same direction and they have the exact same length. So this is why that procedure always is just transforming it back to the origin. So let's put this back where it belongs. It was at, what, 9, 12? All right, so the correct place there. Okay, so then we took the scale factor and we multiplied it by b prime. So the scale factor was 2/5. So this is what we called p prime. So p prime equals 2 divided by 5 multiplied by b prime. So you can see I'm doing that down here, 2/5 times b prime, and that gives us this point p prime, matching what we had before. Now to move back to our line over here, we just added a back to it. So p was equal to p prime, plus a. And that shifts us back onto the segment that we wanted. And you can see the coordinates are right here. Now to verify that we have the ratio that we want, let's come back and put some segments in there. So those segments are named F and G, and what we want is that the ratio of those segments is 2/3. So what we should be seeing is 0.6 repeating, so it'll probably round it to 0.67. So if I do F divided by G, that ratio you can see right there is indeed 2/3, or at least rounded. So this procedure will work in general. This is equivalent to what you're seeing in Play-Doh, but they are making the formula look much more complicated. But if you can understand the basic steps that we just went through here, this always works. So again, let's try to do this in general, without any numbers, just with letters. Okay, so we've started with a general segment, AB, and again, we could make it a directed line segment. Going from A to B, I'm labeling its coordinates as x's with subscripts of A and x's with subscripts of B. This was the same notation they used in Play-Doh. Okay, so the process was, the first thing was to move it back here. So we already know A prime is the origin. We're always moving that back to the origin. B prime was found by doing B minus A. Now we'll come back and actually write this down as a better formula, but let's just leave it like that for now. Then to get p prime, we said it was the scale factor. Well, the scale factor is a over a plus b multiplied by this image point here, multiplied by b prime. Now this one we could write a little bit more cleanly because we know b prime is this. So it's really a over a plus b times b minus a. And again, what this is saying is take the coordinates of b, subtract the coordinates of a, and then multiply it by this scale factor. To get the final coordinates for p, we just have to move this point back up and over with the same translation. In other words, we just need to add a back to it. So p equals all of this, or let's actually write it more simply. It's p prime plus a in general. Just take that point, add a back to it. Or since this is p prime, we could write it as a over a plus b times b minus a plus the a. This is p prime, and we're adding a to it. So this is the formula I prefer to use. This models exactly what the procedure is. We figure out the scale factor, which is always going to be, if this is the given ratio, then a over a plus b is the scale factor. You take your terminal point. This would be the terminal point, the one that's this one is the terminal point, the one with the arrow. You subtract a from it. That translates it down to this point. You then multiply that by the scale factor and finish it by adding a back in. Now, to show you that this is consistent with their formula, let's come back and make this a bit more explicit. When we say b minus a, we're really referring to a point here. We're saying take the x-coordinate for b, so x sub b, subtract the x-coordinate from a, x sub a. You could do the same thing with the y's, so y sub b minus y sub a. This is the ordered pair that's actually represented by that difference. So then this could actually be placed in here. We could write this as a over a plus b times x sub b minus x sub a y sub b minus y sub a. And then this is just a constant, it's just a number, so it could be distributed in. And you can see this is where it just starts to make it really look a lot more complicated than it actually is, just because we have so many symbols going on here. And that's why I don't prefer the formulas that you see in Play-Doh. They're just too hard to keep track of. I think this is much more condensed and hopefully easier to remember. So this is an ordered pair. It tells you how to generate the x-coordinate, how to generate the y-coordinate. And what this represents right now is just the coordinates for p prime. So to get the final answer, we have to take this point and we have to add the coordinates for a back in. So the final formula would be adding a back in, so that's the adding a to the x-coordinate, and then for the y, so just adding y sub a to that. So this was one of the formulas that you saw, but you can also simplify this. If you distribute through here, you get like terms, or you get a common denominator, I should say, and add all of them together and simplify, then it can be turned actually into this expression here, which is the one that I think they wrote on the summary page. You're welcome to use it, but I still don't think it's preferable. It is very condensed, but I think that's just hard to remember this. I think this, for me at least, makes a lot more sense. So we just remember it as find the scale factor, take the terminal point, subtract the initial point, multiply it by the scale factor, and add back in the initial point. And that works every time. It hopefully makes sense geometrically with what you're actually doing, right? To find, first, again, just to go through the steps again, we would start off by taking the terminal point, we would subtract this point. That's what gives us this. We then multiply this point by the scale factor, which gives us the point p prime. Then we shift p prime back to the other line by adding a back to it. And all of that is summarized by that formula there. So let's try to actually apply that. Okay, the problem says find the point P along the directed line segment from point G, which is given by these coordinates, to point H, which is given by this, and we want it to partition the segment in a ratio of 1 to 3. Now you'll notice I got different letters here. It doesn't really change anything, but just to make it maybe more clear and consistent here, let's just relabel these as A and B. And the order does matter. So this is where the directed line segment part comes in. When they say A to B, that means the arrow is pointing at B. So if we label these, this is A, this is B, and the arrow would be here. Right? This is where the directed part comes in. Okay, so if we're going to do the formula, we need the scale factor, which is always A over A plus B. In other words, it'll be 1/4 for this problem. Okay, then let's go right to the formula. So the formula says that P is going to be equal to A over A plus B, scale factor, multiplied by B minus A, the difference in the 2 points, and then at the very end you add A back in. So if we put everything into this, we have 1/4. Then we have to do B minus A. So this is going to be a point here. We're going to start with B, subtract off the coordinates for A. So this is the difference in their x coordinates. Then I have to do the difference in their y coordinates. So -1 minus 3. Order is critical here. It has to be the B coordinates minus the A coordinates. Okay, and then at the very end, we're going to add A back in. So we might as well write it down here. So this is going to be -5, 3. Okay, so got 1/4 out in front still. This is going to give us 6, and that's going to give us -4. And then distribute the 1/4 through, so you're going to get 3/2 and -1, plus now the point -5, 3. Okay, so this is really 1.5. I mean, obviously I would prefer you to stick with the fractions, but if we're going to be graphing, then we might as well change it to a decimal. So when you add these together, this is really going to be 1.5 minus 5, and then -1 plus 3. So the final image point that we get is -3.5, 2. That is the point P. So let's go back. Actually, let's try to just bring the picture down. Okay, so if we're going to go back 3.5 and up 2 units, so we're right there. So if this was A, this was B, this is what we're saying P is. So the idea is that this, if we did the ratio of this to this, we should have the original ratio, which was 1/3. And then also, if you did this divided by the whole thing, it would be 1/4. So you can see the answers don't have to come out perfect. It's probably more common that you're going to get decimal or fraction answers. Let's try one more of these. All right, we've got, says find the point P along the directed line segment from point Q to point R that partitions the segment into the ratio of 3:2. Okay, so again, order matters. So we're going to call this A and call this B, A to B. So if we label these, looks like this one is B and this one is A. So if we were doing a directed segment, it would actually be like that. Okay, so again, we want to do scale factor first, which is A over A plus B. And so that's going to be 3/5. Order matters here too. This is A to B. So 3/5. All right, so point P is going to be A over A plus B times B minus A plus A. So that's 3/5 times, now we need to do the difference in the 2 points. So again, be careful with your order. So -5, take away 12 for the x's, this x minus that x, then -2 minus a -7. How did I get that there? -2 minus a -7. And then we'll put in the A again. So A is 12 -7. So this is the scale factor multiplied by B minus A plus the A. All right, so that's 3/5 times -17 minus, looks like 5, or sorry, it's plus 5. All right, and then bring back down the other point. All right, now distribute through, and you can see this one's not pretty. It's very common for them not to be. So we're distributing it to each one. All right, so that when you add the x's now, add the 2x coordinates, add the y coordinates, you end up with 9/5 and -4. And if we change that to a decimal, that's 1.8 -4. So if we were to plot that, go over 1.8, so not quite to 2, but down 4, and you're going to be right here. And so for this one, the ratio of A to P, this is where again the order matters, A to P, this segment, divided by this segment would be 3:2. And notice too on this one, this is a longer segment, A to P, which is why in the ratio, the first number was bigger than the second one. That's why this segment has to be bigger than the one from P to B. All right, hopefully you find this helpful. Hopefully that helps you do a little bit better on the mastery test. I would love to be able to do this for more of the lessons. Right now, I'm not sure that I will be able to get to more of them. If I have a chance, I will make more of these and try to post them on the YouTube channel. So good luck. Just keep trying your best. I know Play-Doh is not the best, but for right now, this is the best thing we have to work with. So keep sending me emails if you have issues. Take screenshots. I'll try to get back to you as soon as I can with assistance. So we'll see you guys soon.